In this lesson, we're going to explore electron delocalization, resonance, and resonant structures. Delocalized electrons are those that are neither confined to one atom nor shared between two atoms. If we look at a simple molecule like water, we can see that it has two distinct types of electrons. The electrons in the hydrogen-oxygen bonds are each in a sigma bonding molecular orbital. And you can see that those electrons are shared between the two atoms, the H and the O, and that means these are localized electrons. The two lone pairs are each in a non-bonding molecular orbital, and as you can see, each is confined to just the one atom, the oxygen. A good example of a molecule that has delocalized electrons is benzene. Benzene has three distinct types of electrons. Benzene has 6 pairs of electrons that are incorporated into CH bonds. Those electrons are in sigma bonding molecular orbitals, and they're shared between just the carbon and the hydrogen, so those are localized electrons. Benzene also has 6 identical carbon-carbon sigma bonds. Those electrons are in sigma bonding molecular orbitals as well, and so each is shared just between two adjacent carbon atoms. And that means those are localized electrons as well. The remaining electrons on benzene are the 3 pairs that are involved in the carbon-carbon pi bonds. Those electrons are in pi bonding molecular orbitals, and it certainly looks as if each pair of pi electrons is simply shared between two adjacent carbon atoms, and that would mean that those are localized electrons, but they're not. All 6 of the pi electrons in benzene are actually delocalized electrons. But when we draw out a Lewis structure or a KEKULE structure for benzene, we draw those pi electrons as if they were shared only between two adjacent carbon atoms. To understand why those electrons are delocalized, we have to look at the individual atomic orbitals that combine to make the bonds in benzene. Each of the 6 carbons in benzene is sp2 hybridized, and that means that each carbon has an unhybridized leftover p orbital. And of course, it's the p orbitals that overlap to create the pi bonds. If we actually look at the orientations of all of the p orbitals in benzene, we see something quite interesting. If we look at the p orbital on any individual carbon, we can see that it's parallel to a p orbital to the right. And when two adjacent p orbitals are parallel, they can overlap to create a pi bond. But if we look closely, we can see that the p orbital on each individual carbon is also parallel to a p orbital on an adjacent carbon to the left, and that enables a pi bond to form in the other direction. What this means is that each carbon has a p orbital that can overlap in parallel with a p orbital on two adjacent carbon atoms, creating two pi bonding interactions. In other words, there is a pi bonding interaction between every pair of adjacent carbon atoms. But when we draw out a structure of benzene, that's not what we see. We only see pi bonding between every other pair of carbons. In reality, those 6 pi electrons are actually equally shared among all 6 carbon atoms. And because those electrons are not confined to one atom, nor shared between only 2 atoms, they are delocalized. In this case, they're spread out among 6 atoms. In order to explicitly show that there is pi bonding between every adjacent pair of carbon atoms, we actually draw 2 structures for benzene. Collectively, these 2 structures show that there is pi bonding between each pair of adjacent carbon atoms. The 2 drawings are connected with a special double-headed arrow called a resonance arrow, and the 2 drawings are called resonant structures or resonance contributors. It's important to understand what these 2 resonance structures are actually showing. At first glance, the second structure simply looks exactly like the first structure, only rotated or flipped over. We have to recognize that the individual atoms haven't moved when looking at one structure versus the other. So if we look at the top carbon in each structure, on the left structure we can see that that top carbon is pi bonded to the carbon to its left. But in the right structure, that carbon is pi bonded to the carbon to its right. And that's how we have to interpret these resonance structures. Each carbon has a pi bonding interaction between both of its adjacent carbon atoms. Benzene does not have alternating single bonds and double bonds between its adjacent carbon atoms. Essentially, each carbon-carbon bonding interaction is a bond and a half. And we know this is the case because of the actual physical structure of benzene. If benzene truly had a pattern of alternating double bonds and single bonds, then the distance between any two carbons that were double bonded would be shorter than the distance between any two carbons that were single bonded, because a double bond is stronger and therefore shorter than a single bond. But we know that benzene doesn't really have an alternating long bond, short bond pattern. All 6 of the carbon-carbon bonding interactions are the same, and the bond lengths fall somewhere in between a single bond and a double bond. Molecules like benzene that have delocalized electrons are said to have resonance, and this occurs when electrons are shared across 3 or more contiguous atoms. And this is commonly observed in molecules that have pi bonds. It's important to know when a molecule has delocalized electrons. Resonance is observed in 2 similar situations involving extended pi systems. Resonance will exist in a structure with 3 or more contiguous atoms that each have an unhybridized p orbital. In other words, either sp or sp2 hybridization. The simplest example is the allylic carbocation. Each of the carbons in the double bond has a p orbital that allows it to create that pi bond, and then adjacent to that, we have a carbocation, and that carbon is sp2 hybridized because it has an empty p orbital. Those 3 p orbitals combine to make 3 molecular orbitals: a pi bonding molecular orbital, a non-bonding molecular orbital, and a pi anti-bonding molecular orbital. You can see that in the pi bonding molecular orbital, that the p orbital on the carbon in the middle can overlap just as effectively with the p orbital on the carbon to its right as it can with the p orbital on the carbon to its left. So if we place 2 electrons into that pi bonding molecular orbital, those electrons will be shared over all 3 atoms. Resonance is also observed when a structure has 2 adjacent atoms, each with an unhybridized p orbital, next to an atom with non-bonding electrons, like a lone pair. The simplest example of this is the allylic carbanion. If we look at the 3 carbons in the allylic carbanion, we can see that the 2 carbons involved in the pi bond are sp2 hybridized. The negatively charged carbon certainly looks as though it's sp3 hybridized. It's not involved in a pi bond, and it has a full octet, so it has no unfilled orbitals. As drawn, the lone pair would actually be in an sp3 orbital. But remember that hybrid orbitals like sp3 orbitals are lobed and look a lot like p orbitals. And so, according to the hybridization model of bonding, the negatively charged carbon actually adopts sp2 hybridization. That allows the lone pair to actually occupy a p orbital, and that p orbital can now form a bonding interaction with the p orbital on the carbon adjacent to it. And because we now have 3 contiguous atoms, each with a p orbital, we have delocalized electrons. So moving forward, it's important to recognize the difference between a molecule and a drawing of a molecule. If we look at either of the 2 resonance structures for the allylic carbanion, it certainly looks as though the negatively charged carbon is sp3 hybridized. But in the actual molecule, that carbon is actually sp2 hybridized. If we look at the 2 resonance structures individually, you can see that that's the case. In the left structure, the leftmost carbon looks like it's sp3 hybridized, but in the right resonance structure, that same carbon is clearly sp2. When looking at the resonance structures for a delocalized pi system, if an atom is ever drawn as sp2 hybridized, then it is actually sp2 hybridized, even if in some structures it's drawn as sp3. A critical part of dealing with molecules with delocalized electrons is drawing all of the resonance structures for the molecule. Additional resonance structures are generated from the original drawing using the curved arrow notation to show the electron movement between the individual contributors. In order to restrict this electron movement into generating only resonance structures, we need to add 2 limitations. When generating other resonance structures, only pi and non-bonding electrons can move. These are the only kinds of electrons that actually can be delocalized, and those electrons can only be moved towards an atom with a p orbital. So let's try to apply this process to a few simple examples. Let's take a look at this first structure. The first thing we really need to do is to assert that the molecule actually has delocalized electrons. Don't try to draw resonance structures for a molecule that doesn't exhibit resonance. In this case, we have 4 carbon atoms, and the 2 on the right are involved in a pi bond, so they're clearly sp2 hybridized, and that means they have a p orbital and can be a part of the pi system. The positively charged carbon is also sp2 hybridized. It has an empty p orbital. The leftmost carbon is sp3. It doesn't have any unhybridized p orbitals, and it doesn't have any non-bonding electrons, so it can't be a part of the pi system. But this molecule still has three contiguous atoms, each with an unhybridized p orbital. So the delocalized system is confined to those three carbons on the right. Now, according to our rules for generating resonance structures, we can only push pi and non-bonding electrons. And in this case, we have a pair of pi electrons. And we can only move them toward an atom that has a p orbital. And if we look to the left of that double bond, we have a carbon with an empty p orbital. And so we push those pi electrons towards that neighboring atom. And that means those pi electrons will now be shared between that top carbon and the carbon to its left. We draw the new resonance structure with all of the atoms exactly where they were in the original drawing. The only thing that's changed is the position of those pi electrons, which are now shared between the two middle carbons. If we look at the structure on the rightmost carbon has two hydrogens attached to it. And that means that in the structure on the right, it still has two hydrogens attached to it. And that means that that carbon is electron deficient, so it has a positive charge. Now, there can be lots of resonance structures for a given delocalized system. How do we know when there are no more structures to draw? That can actually be difficult to determine in complex systems. If we apply the same process to our new resonance structure, we can see that the only electrons we can move, again, are those pi electrons, and the only direction we can move them is back where they were in the original drawing. A good rule of thumb is that if the only electron movement available simply undoes what you've already done, then there are probably no more resonance structures to draw. Let's look at the next example. Again, the first thing we should do is to assert that this molecule will exhibit resonance, and then find the actual delocalized system. So here again, we have four carbon atoms, and the two on the far right are involved in a pi bond, so they're clearly sp2. And then the negatively charged carbon appears to be sp3. But remember, whenever you have a lone pair adjacent to two atoms that have p orbitals, that lone pair is actually in a p orbital and is a part of the pi system. This molecule is really just a substituted allylic carbanion. The leftmost carbon is sp3 hybridized, it doesn't have a lone pair, so it's not a part of the pi system. But because the molecule has two adjacent atoms with p orbitals next to an atom with a lone pair, this will exhibit resonance. And the delocalized pi system is restricted to the three carbons on the right. Now we know when generating resonance structures, we can move both pi electrons and lone pair electrons. And in this molecule, we actually have both. So there's a bit of an ambiguity as to how we should proceed. We also know that we can only move electrons toward an atom that has a p orbital. So here it's important to make that distinction between the molecule and the drawings of the molecule. If we apply this restriction to the drawing we have, we can see that those pi electrons cannot be moved towards the carbon to the left, because as drawn, that negatively charged carbon is actually sp3 hybridized. And that means as drawn, it doesn't have a p orbital. And when generating resonance structures, we can't push electrons towards an atom unless it has a p orbital. But the lone pair electrons themselves can be pushed towards the right, because the carbon to the right of the negative charge actually has a p orbital, right? As drawn, it's sp2 hybridized. So we can push the lone pair towards that atom. In doing so, we would exceed the octet on that top carbon, and we know that means we need to push electrons off at the same time. And so we push the pi electrons towards the next atom with a p orbital, which is actually the rightmost carbon of the double bond. And that places a lone pair on that rightmost carbon. When we draw the new resonance structure, again, all of the atoms are in exactly the same places they were in the original structure. The lone pair from the original structure is now a shared pi bond between the two center carbons, and the pi electrons from the original drawing are now deposited as a lone pair on the rightmost carbon in the new drawing. And because that rightmost carbon now has 5 electrons all to itself for formal charge purposes, it's now negatively charged. Again, if we try to generate any more resonance structures, we see that the only thing we can do is to undo what we've already done, pushing the lone pair electrons back towards the left, depositing the pi electrons onto that adjacent carbon. In more complex systems that have multiple pairs of delocalized electrons, it's helpful to have a plan to decide which pair of electrons to start moving first. The first thing to look for is an empty p orbital. If the pi system has an atom with an empty p orbital, start by moving electrons toward it from a neighboring atom. If we look at this example, we can see that all 5 carbons are sp2 hybridized, and so all 5 carbons are a part of the delocalized pi system. The pi system actually has 2 pairs of pi electrons, but because this molecule has an empty p orbital as part of that pi system, we now know to start by pushing the rightmost pi bond towards that empty p orbital. Again, if you look closely, this is just a decorated allylic carbocation. When we look at the newly generated resonance structure, we can see that there are actually 2 pairs of pi electrons we can attempt to move. Moving the pi electrons on the far right towards the carbocation would simply be undoing what we've just done. But we can also now move the pi electrons on the far left towards that same carbocation, and that's going to generate a third resonance structure. If we try to generate any additional resonance structures from this third drawing, we can see that all we can do is undo what we've just done. If we look at the next example, we can see that there are no atoms that have an empty p orbital. So the next thing we look for are non-bonding electrons that are a part of the delocalized pi system. And we start by pushing that lone pair towards a neighboring atom with a p orbital. So here, we're going to take one of the lone pairs on the oxygen and push it toward the sp2 carbon to its left. That will create a new carbon-oxygen pi bond and would exceed the octet on that carbon, so we push the pi electrons towards the next atom with a p orbital, depositing them as a lone pair on that leftmost carbon. If you think about it, this is identical to the allylic carbanion. The only difference here is that we don't have a negatively charged carbon with a lone pair. This molecule has a neutral oxygen with a lone pair. We can see that in the new drawing, the oxygen now has 5 electrons to itself for formal charge purposes, making it positive, and the leftmost carbon now has 5, making it negative. If we try to move electrons on this new drawing, we can see that the only thing we can do is to undo what we just did. So in cases where the molecule doesn't have an empty p orbital and doesn't have a lone pair as part of the pi system, your last resort is to simply start on one end of the pi system. This is often encountered in dienes and trienes and similar molecules. So here we have 1,3,5-hexatriene, and this molecule actually has quite a number of resonance structures. We're just going to draw a few of them out to demonstrate the idea of where to start. So if we begin on the far right pi bond, we can push those pi electrons towards the next atom with a p orbital. Pushing those electrons to the left would exceed the octet on that next carbon, so we break that pi bond and deposit the pi electrons as a new lone pair. Since we began by pushing electrons towards the left, we're going to continue pushing electrons towards the left until we can't go any further. If you look at the 3 leftmost carbons, you can see that we have an allylic anion. So we simply push that lone pair to the left towards that pi bond, creating a new pi bond and depositing the existing pi electrons as a lone pair on the leftmost carbon. Since we've pushed the electrons as far to the left as they can go, we now start over again from the original resonance structure, starting from the left end and now pushing toward the right. And we can see that the process is essentially the same, generating 2 very similar resonance structures. Remember that when we draw the individual resonance structures for a delocalized pi system, the real molecule looks like a blend of all the structures. The molecule isn't consistently changing from one structure to the other. It is always a simultaneous blend of all of the resonance structures. It's like a labradoodle. A labradoodle is a hybrid between a Labrador retriever and a poodle. A labradoodle isn't a Labrador retriever half of the time and a poodle half the time. It's always a labradoodle. Now, just because a molecule with delocalized electrons is a simultaneous blend of all of its resonance structures, that doesn't mean that it is an equal blend of all of those drawings. Some drawings, just like some structures, are more stable than others. And more stable drawings contribute more to the real structure of the molecule than do less stable drawings. So let's take a look at just a few of the structural features that can make one resonance structure less stable than others. First is the presence of an atom with an incomplete outer shell, or incomplete octet. So in this example, we have 1,3-butadiene. And if we generate the 2 remaining resonance structures, in each drawing there is a carbon with an incomplete octet, the carbocation. And that means that these 2 resonance structures are less stable and therefore contribute less to the real structure of the butadiene molecule. As a consequence, 1,3-butadiene has more double bond character on its outer carbons than between its inner 2 carbons. Another thing that can destabilize one resonance structure compared to others is putting charges in bad places. Placing a negative charge on a less electronegative atom or a positive charge on a more electronegative atom is going to destabilize one resonance structure compared to another. So here we have a pi system involving a double bond and an adjacent lone pair. Again, this is similar to the allylic carbanion. When we draw out the second resonance structure, we can see that the negative charge has moved from a carbon atom to an oxygen. And because oxygen is more electronegative, it's going to do a better job of stabilizing that negative charge. And that means that the resonance structure on the right is going to be more stable and will contribute more to the actual structure of the molecule than will the resonance structure on the left. In the actual molecule, most of the negative charge is on the oxygen, and most of the pi bond character is between the two carbons. Another thing that can destabilize one resonance structure compared to another is charge separation, the introduction of additional charges. So in this example, we again see that we have a pi system that involves a double bond adjacent to an atom with a lone pair. When we draw out the only remaining resonance structure, we see that we've introduced a pair of new charges. That's charge separation, and resonance structures that have charge separation are typically less stable than those that do not. And again, what this tells us is that most of the double bond character in this molecule is between the two carbons and not between the carbon and the oxygen. Probably the most important aspect of resonance is its ability to introduce additional stability. Resonance generally has a stabilizing effect, and all other things being equal, a molecule with resonance will be more stable than one without. So here we have two dienes. These dienes are isomers, and so they have the same formula. And they also have the exact same kinds of bonds. Each has the same number of CH bonds, the same number of CC sigma bonds, and the same number of CC pi bonds. If we look closely at the diene on the left, we can see that it has 4 contiguous atoms with a p orbital. And that means it has delocalized electrons. It's going to exhibit resonance. And it's called a conjugated diene. The diene on the right also has 4 atoms with p orbitals, but they're not contiguous. And there is no contiguous chain of 3 atoms in a row or more with p orbitals. And so this diene does not have delocalized electrons. It doesn't exhibit resonance. And it's called an isolated diene. Because the conjugated diene has resonance, it's resonance stabilized and is more stable than the isolated diene. That extra stability is called resonance energy or delocalization energy, and it's simply the extra stability introduced because of resonance. Resonance can have a particularly powerful stabilizing effect on charges. Remember that when you spread out charge, you stabilize charge. Let's take a look at some examples where resonance can stabilize a negative charge. Anion stability is really important in acid-base chemistry. If a negatively charged base is stabilized by resonance, that means that its conjugate acid will be considerably more acidic than in a similar molecule that lacks resonance. So if we look at the allylic anion is the conjugate base of propene. And because the allylic anion stabilizes that negative charge by spreading it out over 2 atoms, the allylic anion is a relatively stable conjugate base compared to a similar system that lacks that resonance, something like propane. And that means that the allylic hydrogens of propene are considerably more acidic than any of the hydrogens on propane. A similar effect is seen in the benzylic anion. A benzylic anion is simply a carbon that is negative adjacent to a benzene ring. The conjugate acid of the benzylic anion is methylbenzene, also called toluene. And because the benzylic anion can spread out that negative charge over several atoms through resonance, it means that toluene is actually considerably more acidic than a similar system like methyl cyclohexane that lacks that resonance. A carboxylate is the conjugate base of a carboxylic acid. And because a carboxylate can spread out that negative charge over 2 oxygen atoms, it means that a carboxylic acid is considerably more acidic than a similar system that does not have that resonance, something like an alcohol. A similar effect is seen in a phenoxide. A phenoxide is simply the conjugate base of a hydroxybenzene, also called phenol. But again, because the phenoxide can spread out that negative charge over several atoms, it means that a phenol is considerably more acidic than a similar system that lacks that resonance, something like cyclohexanol. Resonance can also stabilize positive charges, and this effect is particularly important in stabilizing carbocations. The examples I have here show the 2 most important resonance-stabilized carbocations. We've already seen the allylic carbocation, which is simply a positively charged carbon adjacent to an alkene. Because the allylic carbocation spreads that positive charge out over two carbons, it greatly stabilizes the positive charge. A similar system is the benzylic carbocation. This is simply a positively charged carbon bonded directly to a benzene ring. And again, because the benzylic carbocation can spread that positive charge out over several atoms, it greatly stabilizes that charge. If you look at these two examples, each is a primary carbocation. But because these two carbocations have resonance stabilization, it's more thorough to describe them as primary allylic and primary benzylic, respectively. A good rule of thumb is that the resonance adds the stability of about one additional degree of substitution. So a primary allylic carbocation has about the same stability as a secondary aliphatic carbocation. And a primary benzylic carbocation, again, has about the same stability as a secondary aliphatic carbocation. The term aliphatic simply refers to a carbon that's not involved in resonance or any pi bonding.